do not butcher this at all. But it's Dr. Bar-Natan. Did I say that right? Does anyone want to confirm?
Bar-Natan. I'm the authority.
Okay, nice to meet you. Dr. Bar-Natan.
I'm the authority on how to pronounce my name, not on anything else.
That'd be great, thanks. Well, Doctor, so I'm just gonna do a quick intro before we get started on the talk, and I think we'll also wait a couple minutes if I don't know if the other admins think that's a good idea. If you want to wait before I give an intro.
Actually, can I just check, Professor Bar-Natan, may I record your talk, and if so, could I post it on the website, or should I not record it?
Yes, you may, and in fact I will record it. In fact, I'm already recording independently.
Oh, perfect. Thank you so much.
Okay, that's awesome.
So I don't think we really need to wait. I think we saw a couple people joining at the end of the demonstration.
Okay, great. So I guess I'll just do the introduction. Just like a quick reminder, so the talk is supposed to be about 55 minutes long, so we would end at 4:55. That includes questions from the participants. And so just a little bit about Dr. Bar-Natan. He is from the University of Toronto, and he will be presenting a talk called Nobody Solves the Quintic. So I will post the abstract in the chat here, which is, it's already on the screen, but I can post it in the chat as well. And then also, there is a handout that he's requested that the participants have on hand. Which I can also send the link to that, but I think that's also up on the screen as well. We're extremely honored to have him here. We were so excited to hear what Dr. Bar-Natan has to say, and we hope you guys enjoy the talk.
So I'm not starting yet, right? I'm supposed to start at 4 or 5, or am I wrong?
Yeah, we can. Wait a couple minutes. What do the other admins think?
Anyway, I want to say a few preliminary things. So first of all, wait, is technology working? Do you hear me?
Mm-hmm.
Okay. Second, so I'm actually feeding twice. So one feed is this, is a screen share. And another feed is a video camera pointing at the screen and mostly showing the screen, but also showing me. I think most of the time the video camera would be the better feed because, you'll be able to see what I'm pointing at, right? I'm pointing at Canadian, and if you're looking at the screen share, you can see what I'm pointing at. So most of the time, try to watch the camera. I hope you can switch between the two. And people should be able to do that. And another thing that I want to say, so if you can hold a copy of the handout, that's great. If you can't, well, it's not the end of the world. I'm happier if I can see you. So you don't see it, but I have a monitor in front of me that shows you. And I'd like to know if you're smiling or crying or are you miserable. So basically, the more of you have video on, from my perspective, the better. However, better you keep the microphone off unless you want to ask a question, because otherwise it gets messy and noisy. I haven't started yet, by the way. I'm waiting for the instructions to start.
We can. I think most people that wanted to join the talk have joined.
Okay.
It seems like we have 38 participants. So if you do want to start right now, I think we are ready.
So I'll start also with an apology about technology. So it's untested technology. I hope everything will work. There will be some glitches inside, I know. And the last thing is I'm not going to follow the chat. And now content. So I hope many of you are undergraduates in mathematics. When I was an undergraduate in mathematics, or even before that, I remember hearing this very romantic story about Évariste Galois, a French mathematician who died at the age of 21, and in a duel. And the night before he died, he wrote up his big theorem, which was, which included the fact that you could not solve equations of degree 5, polynomial equations of degree 5. And it was always sort of something that I perceived as one of the great achievements of mathematics. How can you show that you cannot solve an equation using the basic operations and roots? How can you show that there isn't a formula to solve an equation? Whereas there is a formula if the equation is only of degree 4. So what's going on here? And for me, it was a second or third year class where I learned why you could not solve the Quintic. And it's a very hard class. It's like the sort of a deep algebra class where you learn about algebraic extensions and Galois theory and group theory and the fact that the symmetric group, or maybe the alternating group, is not solvable, and lots of stuff. And relatively recently, just a few years ago, I learned that there is a much easier topological proof that you can present to practically anyone, and my hope is to show you this proof today. Okay, so the only prerequisites are you need to know the first week of group theory. So basically you need to know what are permutation groups, and you need to know how to compose permutations, but you don't need to know anything about the permutation group otherwise. And the other thing is you need to understand that every complex number has n roots, n order n roots, so it would have 7 roots of order 7, and you need to know how they behave, how to compute them, what the 7 roots look like. These are the preliminaries. I'm not going to say much more about them, and let's move to the next page. So again, I'm hoping you're all holding a copy of this handout, and again, if not, it's not the end of the world. And again, here is, and maybe I'll start with a few definitions. So something very useful that occurs in many places in mathematics, maybe at the end if I'll have time, you'll ask me and I'll give you a few more examples, is the commutator of two operations. So if you have two operations A and B, their commutator, A bracket B, is A, B, A inverse, B inverse, or in plain English, it means you do the operation A, then you do the operation B, then you do the reverse of A, so you undo A, and then you undo B. And here are a few examples. So in the integers, if I'm thinking of m or n as add m or add n, then the commutator of m and n is equal to 0. Right? And the reason is, well, if m and n are, say, 2017 and 729, then plus 2017 plus 729 minus 2017 minus 729 is equal to 0. Okay? And it is 0 because of the commutative law. Basically, the fact that I can switch the middle two terms implies that at the end you get 0, right? But not always not everything is commutative. So here is an example where the commutator is not equal, is not the do-nothing operation. So in the permutation group of order 3, the commutator of the cycle 1, 2 with the cycle 2, 3, I claim is equal to the cycle 1, 2, 3. Maybe I'll remind you what these things mean. So the cycle, but this will be visible only on the video, not on the screen share. Okay? So the cycle 1, 2 means the permutation that swaps 1 and 2. So it's the permutation that maps 1 to 2, 2 to 1, and leaves 3 in place. So 3 stays in place. Do you see that? Is this visible? Similarly, the permutation, the cycle 2, 3 means the permutation that swaps 2 and 3. So 2 goes to 3, 3 goes to 2, and 1 stays in place. And finally, the cycle 1, 2, 3 is the permutation, so maybe I'll write it up here. So 1, 2, 3 is, well, each one goes to the next and the last one goes to the beginning. So 1 goes to 2, 2 goes to 3, 3 goes to 1. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. And now let's compute the commutator of these two. So again, I do 1, 2, then 2, 3, then 1, 2 inverse. The inverse of 1, 2 is just 1, 2. If the operation is to swap 1 and 2, the inverse is to swap them again. And then 2, 3 inverse, which means again, which again is just 2, 3 once again. And now let's see what happens. So suppose I start with 1. 1 goes to, so under 1, 2, 1 goes to 2. Under 2, 3, 1 goes to 3. Under 1, 2, 1, 2 inverse, so 1, 2 inverse is just 1, 2, but 1, 2 doesn't touch 3, so it stays 3. And then 2, 3 inverse maps it to 2. So overall, 1 went to 2 by the commutator of these two operations. And so as advertised, as I promised that 1 would go to 2. Is this visible, by the way? Good. And you can check similarly that 2 will go to 3 and 1 will and 3 will go to 1. And well, that's the end of the example. So not always a commutator is trivial. Right? The resulting thing here is not a trivial permutation. And by the way, the same thing is true in general. So the cycle ij, commutator with the cycle jk, is the cycle ijk, where ij and k are any 3 distinct integers between 1 and n if I'm working in the permutation group Sn. Okay, here's another example. The cycle ijk, commutator with the cycle jkl, in any permutation group of order greater than or equal to 4, I must be in a permutation group of order at least 4, because I want I, j, k, and l to be distinct. If I want to have 4 distinct numbers, I must be in a permutation group of order greater than 4. So I claim that the result is the product of the cycles IL and JK. In other words, I get swapped with L and J gets swapped with L. I with L and J with K. So let's test it. And again, I'll test it on just one thing. I don't know. Let's check it. Let's test it on J. Let's see what happens to J if I apply to it these 4 operations. So under the first operation, J becomes K. Then under the second, K becomes L. Then I go backwards, but L is not even appearing here, so I'm still with L. And then I go backwards and L goes to K. So overall, J went to K as advertised right here. And you can check the rest. And all of this is uninteresting nonsense. Here is what's really important. What's really important is that in a permutation group of order greater than or equal to 5, the commutator of ijk with klm, well, for this to be, for me to be even be able to speak about this commutator, I have to, I must have at least 5 numbers, ijk, klm, sorry, ijk, l, and m. And by the way, this 5 is, this 5 is exactly the 5 of the quintic. That's where the 5 comes from. Anyway, so I claim that the commutator of ijk with klm is jkm. So let's test it. Again, it's a bit boring, but let me do it. So let's see. I goes to, under ijk, I goes to j. Then under klm, j doesn't even appear here. J stays in place, so j stays in j. Then under ijk inverse, so I go backwards, so j becomes I. And then under klm, so klm doesn't even touch I, so I stay at I. So I goes to I, which is consistent with what's written on the right-hand side. I guess my choice of testing was a bit uninteresting. It was a number that doesn't get moved. Let's try another one. So let's try j, okay? So j goes to, so under ijk, j goes to k. Under klm, k goes to l. Under ijk inverse, l stays in place. Under klm inverse, l goes backwards to k. So j over all goes to k, as advertised right here. And you can check that the rest is true. But the point here, and forgive me, I know it doesn't look like I'm proving one of the most impressive theorem in mathematics. We'll get to it. It starts as sort of tiny computations, and quickly it will become much more interesting. So anyway, the point here is that the commutator of two things, of 3 cycles, is of the same type, is again a 3 cycle. This was not the case in the previous examples. In the previous example, the commutators of 2 things of one type came out something of a different type. Furthermore, that thing that appears here, jkm, well, by choosing j, k, and m to be whatever numbers I want, I can make the right-hand side be whatever I want. So the conclusion is that every 3 cycle in S5 is the commutator of 2 other 3 cycles. So for example, 1, 2, 3 is the commutator so here, 1, 2, 3 is the commutator of 4, 1, 2 and 2, 5, 3. But 4, 1, 2 in itself can be presented as a commutator. So 4, 1, 2 is the commutator of 3, 4, 1 with 1, 5, 2. And likewise, 2, 5, 3 is itself a commutator. It's the commutator of 1, 2, 5 and 5, 4, 3. So 1, 2, 3 not only is the commutator of 2 things, of 2 permutations, in fact it's the commutator of 2 commutators. But each of these, 3, 4, 1, 1, 5, 2, 1, 2, 5 and 5, 4, 3, in itself is a commutator. So I could write 1, 2, 3 as a commutator of commutators of commutators. But again, each triple that appears here is again a commutator. So I could write 1, 2, 3, like here, as a commutator of commutators of commutators of commutators. And of course I could continue. Questions, comments? Why is it related to solving the quintic? We'll see in a minute, but I hope it makes sense. Okay. I think I'm done, and let's move on. So, right, here's the main theorem. This equation, you do not have a formula for the solution of this equation, the order 5 equation, ax to the 5 plus bx to the 4 plus cx cubed plus dx squared plus ex plus f is equal to 0. So you do not have a formula for the solution which uses only operations on a scientific calculator, namely plus, minus, times, divide, and the nth root. I mean, I'm not going to show it, but if you use sines and cosines and exponentials and logarithms, it's not going to help you. Okay? The history, as I mentioned, starts with Abel and Galois in the early 1980s. And the solution I'm going to present today, the proof that I'm going to present today, is due to Vladimir Arnold from the early 60s, and here are some references. In particular, I learned about it from a very short YouTube video, here's the link, made by a former student of mine. So a former student of mine made a video for the proof and then sent it to me, and well, I was so excited. Anyway, let's learn some more. So first of all, oops, looks like I jumped two slides at once. Right. So first of all, let's see how you solve the quadratic equation. So I didn't list it as a preliminary, but I think it's high school material. Is it safe to assume that everybody knows how to solve ax squared plus bx plus c is equal to 0? Well, good. The formula is lambda 1, 2, the two solutions are given by minus b plus or minus the square root of b squared minus 4ac divided by 2a. When I was in high school, it was called the Munster formula. Was it also called the Munster formula in your high schools? I don't know. It's kind of a monster, but it's a tiny, tiny, tiny monster relative to the monsters we're going to see in the next few pages. Okay? So, but even a monster, it's better to divide it into steps. So I'm calling the thing inside the square root, so b squared minus 4ac, I'll call uppercase delta. Then the square root of this is, so the square root of our uppercase delta, I will call lowercase delta. And then the result, r, is minus b plus lowercase delta divided by 2a. Okay? And let's see how it works. So I made a little animation, and I hope it's not too glitchy. So here is an input complex plane. So all of these numbers, a, b, and c, could be complex numbers. And at the moment, a is equal to 1, b is equal to 0, and c, I don't know, looks like I times 1/3 or something like that. Okay? And when you feed these into the formula, delta comes out here. I hope you can see it. It's kind of tiny. Please watch it at full screen. And then the square root of delta comes out here. And when you feed everything into r is equal to minus b plus delta divided by 2a, the output is here. And now, if I'll start moving a, b, and c, so if I move c, uppercase delta moves, maybe I should move to the other side. So if I move, this time I'll move a. If I move a, uppercase delta move, lowercase delta moves correspondingly, and finally the solution moves. Now, you should not be convinced because, well, I just showed you that things move, but I didn't test that this actually solved the equation. So let's test that it solves the equation. So what I did now is I kind of moved with the input one step backward. So here are lambda 1 and lambda 2. If you know lambda 1 and lambda 2, it's very easy to write an equation whose solutions are lambda 1 and lambda 2. Namely, and again this will appear only on the video feed, not on the share screen. So namely, you write x minus lambda 1 times x minus lambda 2. You open the parentheses. What is it called? The LIFO rule? No, the FOIL rule, right?
Foil.
Right. You open the parentheses and it comes out ax squared plus bx plus c for some a, b, and c. In fact, a in our case always comes out 1, the way I did it, but that really doesn't matter. And what I can do is I can feed these a, b, and c into the machine from the previous slide and see what comes out. And if we're lucky, what comes out is one of these lambdas. So indeed, if you look at the output, the black dot here, I hope you can see it, it is pointing at lambda 2. So the formula finds the solution lambda 2. And if I'll move lambda 2, if I'll move lambda 2, it doesn't want to move. Oh, now it wants to move. Then A, B, and C move, but notice that A doesn't move because A is always 1. Delta moves, lowercase delta moves, the output moves, but the output always traces my finger with a little bit of a lag because my computer is not perfect. Are you with me? Have we verified the solution of the quadratic? I need to see, I see now 10 or 11 faces. Smile, say yes, say no, cry, and I'll go away. Okay, good. Well, that was the quadratic. But now I want to say something interesting. So, the square root function is a bit problematic. Here's a machine that computes the square root function. And by the way, I could have talked about the nth root in exactly the same language. So here is the input. When the input is 1, the output is 1. Okay? Can you see it? Good. Now when I move the input towards, say, I, the output is in 45 degrees to the positive x-axis, as you should know if you've seen roots of complex numbers. Then I can continue moving the input towards -1, and the output moves towards I. But you see, there are actually 2 square roots for any number. And the first one and the second one, which is the negative of the first. So equally well, the output could have been here. Okay? And there is no continuous way to move the output as a function of the input. So if I'll move the input down below the x-axis, all of a sudden the output jumps to negative I, right? So if the input is -1 plus a little positive imaginary number, or I times a positive number, the output is very near I. And if the input is just below the real axis, the output is very near negative I. That's the nature of the square root function. So here is a variant, the persistent square root function. So the persistent square root function isn't really a function. What it is, it's more, people who know topology will call it path lifting or something like that. But what it really is I'm telling the computer, every time you are asked what is the square root of a number, please remember the answer. And then the next time you are asked, if you are asked about a number which is close to the previous one, give an output which is with the same sign, which is close to the previous output. So that's not really a function because it's a function with memory. So if I move the point, the input, the computer remembers what output it gave and gives an output which is close to the previous output. So if I spin around the input, the square root function occasionally jumps. Now, and now. But the persistent square root function keeps moving continuously. Are you still with me? Okay. Here's an example of sort of persistence somewhere else. So I don't know, maybe you've watched the series Yes, Prime Minister, a lovely British series about the British politics. And here is one of the famous episodes in which Sir Humphrey, the very wise civil servant, is explaining to the minister, Bernard Woolley, who is, as you can expect from a politician, not terribly smart. So he is explaining how asking questions in a sequence while modifying them just a little bit can give you completely opposite answers. So more or less like the square root function. If I, so if I move the square root function, if I move the input from here to, sorry, why did it stop moving? I don't know. Oh, here. No. If I move, it stopped. Okay. If I move the input a full circle, the output of the persistent function goes to its negative. So now it's on the right. I move a full circle, it goes to the opposite end. Right? So you're welcome to read this. And even better, let's try to play it, and I hope the technology works. And so, I don't know, my computer decided to act up. Well, I have a mouse. Let's see if the mouse will help. Sorry about that. Oops, it's frozen. Why is it frozen? I'm sorry about that. I am not sure what's going on. Let's try the keyboard. Oh, good. At least something is working, and let's hit play, and nope. Oy, 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 sorry. Technology is not always what you want it to be. And let's hit play now with the mouse.
You know what happens? A nice young lady comes up to you. Obviously you want to create a good impression. You don't want to look a fool, do you? No. So she starts asking you some questions.
We can hear what they say.
Mr. Woolley.
Oh, you cannot hear?
Are you worried about the number of young people without jobs?
Yes.
Sorry?
Are you worried about the rise in crime among teenagers?
Yes.
Do you think there's a lack of discipline in our comprehensive schools?
Yes.
Do you think young people welcome some authority and leadership?
Sorry, we can't hear the audio
Yes.
from the
Do you think
video.
they respond to the challenge?
Yes.
Would you be in favour of reintroducing national service?
Is that coming out 3 years or?
I'll have to apologize. Read it when you get a chance. It's fun. Sorry. Anyway, let's move on. Of course, it's not really a part of the proof, and see how the cubic is solved. So, well, here is the formula, a bigger monster, to solve the cubic. So if you have ax squared plus ax cubed plus bx squared plus cx plus d is equal to 0, and you want to find r, the solution, well, you set uppercase delta to be minus 18 abcd plus 4b cubed d. Well, I'm not going to read it to you, there's nothing particularly interesting about it. Then you set lowercase delta to be the square root of uppercase delta. Then you set uppercase gamma to be this funny expression written here. Then you set lowercase gamma to be the cubic root of uppercase gamma over 2. And then the solution is given by this formula. And like before, I could animate it. So I could essentially build a machine. So the inputs are A, B, C, and D. In the first picture of the complex plane, I'm showing the output delta. In the next picture of the complex plane, I'm showing the square root of uppercase delta. So in fact, if delta is here, its square root comes out to be here. Then I compute uppercase gamma from delta. Then I compute lowercase gamma being the cubic root of lowercase delta, of lowercase gamma, of uppercase gamma, and then I compute R using this formula, and it's a messy machine, and when I move the inputs, the output moves. Now I'm moving them with the mouse, but I suppose you can still see it. And again, let's test it. So here is the same machine, but pre-composed with the machine that takes 3 numbers and produces the cubic equation whose solutions are these 3 numbers. Namely, I look at x minus lambda 1 times x minus lambda 2 times x minus lambda 3, open the parentheses and write it as ax cubed plus bx squared plus cx plus d. So here are lambda 1, lambda 2, lambda 3. Here are a, b, c, d. Here is delta, here is lowercase delta, here is gamma. It came out a bit far away from 1, so the whole square around 1, the whole unit circle is here and gamma is here. Here is the cubic root of gamma, and here is R. So let's start to move things. So if I move any one of the roots, everything moves. The whole machine is in motion. But the nice thing is, well, at this given time, I have used the formula to compute the roots, or one of the roots, of the equation whose 3 roots are here. So that root must be one of the 3. And in fact, R is pointing to the one at the bottom right. And since I'm using persistent roots, if I'll move any one of the inputs, R will move correspondingly, but basically R must be a solution close to the previous solution. So if I'll move this one, R will move, maybe I'll use the mouse. If I move this one, R moves in a corresponding way, while if I move any of the other 2, R just stays in place. Okay? Well, here's how you solve the quartic equation, the equation of degree 5. So, I don't think I want to read it out to you. And if I wanted to expand it, it would be a truly horrible monster. And again, but this monster becomes a machine, right? It's a machine in which if I move the inputs A, B, C, D, and E, well, the results of the first stage move, then some square root is computed and the result is moving, and then, well, I mean, I don't think I want to, I think the nature of the machine is clear and there's not much point in actually visualizing it. Let me only test that this actually solves the problem. So if I start with 4 roots, feed them or create the equation whose roots are these 4 numbers using the same trick as before, feed this equation into the machine, the output is right here, which is one of these numbers, and if I'm moving any one of the roots, the output doesn't move, but if I move the input which that the output was pointing at, then the output moves correspondingly. So this crazy machine actually solves the equation of degree 4. I hope you're still with me, because now is the theorem. No such machine exists for the quintic. Okay? So, here is, sorry, I need a key point. The key point is that, well, let me say it in words, the persistent root of a closed path is not necessarily a closed path, yet if a closed path is the commutator of two closed paths, its persistent root is again a closed path. So let me explain it. So let me explain it using the 10th root. So here is a machine computing the persistent 10th root. So if I move the input around the complex plane, the output moves at 1/10 of the radial velocity. That's how roots work. I'm hoping, I mean, that was one of the preliminaries. I'm hoping you know this. So again, if I move the input, the output moves at 1/10 of the rate. In particular, if I start here and do 10 circles, the output will return to where it was. Well, maybe I'll stop. I mean, I think you can see it. I don't need to do it in detail. Now, if the input moves along a closed path, so say I start here, move the input all the way around and come back, the output does not move along a closed path, because the output moves just 1/10 of a rotation. Okay? However, if I do a commutator, so suppose I move, let me bring the input back to the beginning. Suppose I move the input, twice in this direction, then 3 times, then 3 times backward, then twice backwards, and then 3 times backwards. Okay, so I'll move the input twice, the output twice around. The input did not come to the back to the beginning. Sorry, the output did not come to the back to the beginning. Now I'll move it 3 more times. The output did not come back to where it was. But now if I'll move it twice back, and then 3 times back, the output came back to where it was. And why is it? Basically because addition of angles is commutative. Okay? So if you add 2/10 of a rotation to 3/10 of a rotation, and then subtract 2/10 of a rotation, and then subtract 3/10 of a rotation, you came back to where you were. And finally the proof, and the whole proof fits on one blackboard, and I still have 17 minutes, so that's plenty of time. So suppose there was a machine, so suppose there was a formula for the solution of the quintic. Is this readable? Good. So suppose there was a solution to the quintic. Namely, there was a machine like the machines we've seen before. And I would create the same testing scheme as before. So I will start with the complex plane and mark on it the numbers lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. These are the roots, or the roots of an equation that I'm going to create. Then I'm going to apply a map C, which goes, so actually the input is in the complex plane to the power 5, right? Because it's 5 complex numbers. Now I'll find the coefficients of the corresponding quintic, and it has 6 coefficients, A, B, C, D, E, F, and so the output is in C to the 6. And now I'll apply the solution machine, which I claim does not exist. So, first of all, I apply a few polynomials to the inputs. So, I may as well still save the inputs for use later, not the inputs, the coefficients for use later. So A, B, C, D, E, F still appears here. But I've computed 3 new quantities, U, delta 0, and delta 1, by applying some polynomials. Then I take a root. So I take the nth root of delta 0 and it comes out delta lowercase delta 0. And you know, I didn't want the box here to be too cluttered, so I put 3 dots to mean that I still save all the other numbers because I can still use them in the rest of the formula. Then I apply some polynomials and get some new numbers. Then I apply some roots and get some new numbers. Then I apply a polynomial. Then I alternate applying polynomials and taking roots. And at the end, my formula points at a certain place R, and R is one of the roots. Okay? And yeah, I see that. And suppose and the machine has the property that if I move the input lambda 2, then everything moves in a crazy way, but at the end R follows the motion. So if I move lambda 2, R follows in exactly the same way. Okay? I'll argue that it leads to a contradiction. So let gamma 1 up 1 up to gamma 16 up 1, so level 1 gammas running from 1 to 16, so I have 16 of them, be musical chair paths in x0. So what are musical chair paths? These are paths in which the input lambdas permute their positions. So lambda 1 goes to lambda 3, lambda 3 to lambda 2, and lambda 2 to lambda 1. Or something like that. Or some other permutation. And in fact, I'll take the permutations from the first slide. So the 16 permutations whose commutators of commutators of commutators of commutators were the permutation 1, 2, 3. And then let gamma 2, the level 1 commutator, be the gamma 2, 1 be the commutator of the level 1, gamma 1, and gamma 2. Gamma 2, 2 will be the commutator of the level 1, gamma 3, and gamma 4. And perhaps it's best if I'll demonstrate it with a picture. So, why isn't it moving? Oy, oy, oy. Sorry, I want to go to the next slide and my computer is not happy about this. Okay, so here is the picture. So oh, okay, maybe now it will work. I'm sorry. Okay, so here is the picture. So sorry, I'm again having technology issues. Okay, are you still seeing this? Okay, so gamma 1 corresponds to the gamma 1 level 1 corresponds to the permutation 2, 3, 4. What it means is that I look at the complex plane and draw the roots lambda 1 up to lambda 5. So let's say they're in a row, so lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. And this path moves root number 2 to be in position 3, root number 3 to be in position 4, and root number 4 to be in position 2. So root number 1 will move to position 2, root number 3 will move to position 4, and root number 3 will move to position 2. So I draw it as a braid in 3 dimensions, but the third dimension is really time. So as time flows from the top to the bottom, I see a dance of roots in which these 3 roots trade places. Similarly, gamma 2 will be the dance which corresponds to the cycle 451. So in pictures, it's this cycle. Gamma 3 will be the cycle 315, and so on. And then the level 2 commutators, so this dance is the commutator of these 2 dances. This dance is the commutator of these 2, this one is the commutator of these 2, and this one is the commutator of these 2. And what it means is, well, if you look at this dance, if you follow from the top to the bottom, well, in the initial segment, I do exactly that. Then in the next segment, I do that. Then I do this one backwards, and then I do that one backwards. And similarly, this one is the commutator of these 2, this one, and so on. And then I'll create the level 3 commutators, and so the level 3 commutator number 1 is the commutator of these 2, the level 3 commutator number 2 is the commutator of these 2, and finally, the level 4 commutator number 1 is the commutator of these 2. So it's a huge mess, but this mess really represents a way in which these roots dance. And let me go back to the previous slide, and I hope this time the computer will allow me to do it. Let me go back to the previous slide, and now comes the punchline. So I have a whole huge collection of paths, and I let the roots dance following these paths. Each of these paths becomes closed when I look at it as a motion here, because the paths just permute the roots, and if you have an equation whose set of roots is the same, it's the same. So if you only permute the roots, it's the same equation. Basically, if you expand x minus lambda 1 times x minus lambda 2 up to x minus lambda 5, and you only permute the lambdas, by the commutative law, the coefficients will be the same. So at this point, all of the paths are closed. Now you apply polynomial to them, they remain closed. Polynomials are single-valued functions, there's no problem. Now you take a root, and the paths at the top level, the level 1 paths, may become open, but their commutators, I see it, but their commutators will become closed, because we know that roots take the commutator of 2 paths, of 2 closed paths, to be to a closed path. So after the first root, the commutators of the level level 2 paths remain closed. Then you apply polynomials, and the level 2 paths are mapped to closed paths. And then you apply another root, and the level 2 paths may open up, but the level 3 paths remain closed, and so on. And since I had more levels than roots, at the end, the bottom path, the final horrible dance that we had at the very end, becomes a closed path. So at the very end, the lowest level remains a closed path. But that's a contradiction. On the one hand, it's a closed path. On the other hand, the overall commutator of commutators of commutators was the permutations that permuted 1, 2, and 3. So 1 goes to 2, 2 goes to 3. So in particular, if R was pointing at lambda 2, it must at the end point at lambda 3, which means that it isn't a closed path. That's it. I apologize for the glitches. Well, any questions?
Okay, so I think from what we've seen, I don't think there's any questions. Are there any questions for me? No, there is. Okay, so you think Neil has any questions?
Yes.
Oh, I have a small question. So it's a contradiction because when you permute these three roots, the path only didn't trace a full circle because you go to another route, but then at the end the R gets permuted in a closed path.
So again, on the one hand, these 5 roots follow a huge, insanely complicated dance, like the dance that was shown in the dance of roots picture. So like this dance, okay? Now, if this dance here, okay? If you trace any particular route following this dance, well, we've computed it at the beginning. This dance is the commutator of these two, which are the commutators of these two and these two, and so on. So at the end, route number 1 goes to be route number 2. If you trace 1 and follow it, it goes to be number 2. So it's not a closed path. So if R is always pointing at lambda 2, and 2 goes to 3. So if R is always pointing at 2, then at the end then after the whole dance, R will be pointing at 3. So it didn't make a closed path. It started in one place and it ended in another. However, seeing that it's a commutator of commutators and commutators and commutators and of commutators, and you're feeding it into a machine in which commutators become closed paths, it must be a closed path, and that's a contradiction. Yeah.
That's really cool.
Yeah, thanks so much for all
Okay.
that. I think because of time, we don't actually have time for any more questions. But we really did enjoy your talk. Thank you so much.
Thank you.
Dr. Bar-Natan. That was amazing. So I think, the clap reaction, everyone can do that, that'd be great. So I think for now, this is like our last thing that we're doing for a while until our social, I believe, is at 7. So for the participants, feel free to, I guess, leave the call, and I guess you can come back, join the same link at 7 for the socials. But other than that, for today, I think we are done with the talks and the keynote speakers. And yeah, thanks so much once again to Dr. Bar-Natan for that amazing talk. That was awesome.
And thanks so much for everyone for coming and listening to the keynotes. Please come to our social, it'll be super fun.